So this first page is a reference page, and I'm going to write that down. And what you want to do is use this first page as a reference when you're graphing things. So you reference these graphs for the shapes of common functions. And you'll see in this section, what we do is we start with the general shape of what a function looks like, and then we graph it by shifting it around based on the information in the following pages. And so what I want to just start by doing is sort of just going through each picture and pointing out like the pattern. Right, so first of all, linear functions are straight lines. We already knew that. The power function is the one I want to focus on first, which is that we have x squared that looks like a u, x cubed does that opposite thing, x to the fourth looks like a u again, x to the fifth does the opposite thing, and so in general, if we have x raised to an even power, it has a u shaped. Okay, so x to the 6th would look like this, x to the 8th would look like that, right? X to the 20th would look like that. And in general, x raised to the odd power, whoops, not xo, but x raised to the odd power is going to have the other kind of shape. And so that's what you should be taking away from this second row. X to the odd power looks like that. Okay? And we get a similar kind of thing in the next row. These are the root functions. And I know, in order to get this on one page, I had to kind of zoom out, and so the graphs are small. But you can look at your own paper if you want to get a closer look. But the root functions, you can see that the even roots look like this. They have this kind of shape. And the odd roots have this kind of shape. Very similar to the way these guys work. And so, the square root looks like this. 4th root looks like this. 6th root would also look like that. 10th root would look like that, etc. Okay? The reciprocal functions isn't one we see a lot, but you will see it a little bit, especially in the homework. And this is showing you the difference between 1 over x and 1 over x squared. And so in general, I'll use some color this time, 1 over x to the odd power looks like this. And 1 over x to the even will look like the other one. Right, so in general, 1 over x to the odd looks like that, and 1 over x to the even looks like that. So keep those in mind. As we keep going down the page here, you can go ahead and cross out the greatest integer function. This is just kind of a weird special case. The reason I put this one in is because we do want to know what the absolute value looks like. Absolute value is one we will see and we will graph. And so the difference between the absolute value function and the, say, even-powered functions up here is that these ones, the absolute values form a 90-degree angle. Okay, that's like a 90-degree angle there, where the other ones have a curved bottom. So if you're looking at a graph and you're wondering whether or not it's an even-powered, x raised to the even, or you're wondering whether or not it's absolute values have corners. And these ones have curved bottoms. Okay? And so what we're going to do on the pages to follow is we kind of start with one of these general shapes, and then depending on what the problem looks like, we move that shape around the xy axis. So you'll see what I mean, and you want to use this as a reference. I'm going to use this as a reference, and so it's just nice to have this one handy. As we go forward here, there's 3 things that I'm looking for when you graph something. Every graph needs the following things. So when I go and I graph or I grade a quiz or a test, I'm looking for these 3 things. Number 1, the correct shape. That's where this page comes in. Looking for the shape to be correct. I'm also looking for any stretches or shifts. You'll see what I mean when we start doing this. And the third thing that I'm looking for you to show on a graph is any intercepts. So any x and y intercepts. So keep that in mind when we're doing this, and I will do those 3 things when we go through. Now, this might be a good time to mention, the homework for this stuff is different than what tests and quizzes will look like. because the homework's online, you can't draw things on the computer, and so these homeworks oftentimes end up being multiple choice, where it gives you a graph and then asks you to write the equation, or maybe it gives you an equation and asks you to match it up with a graph, or it asks you to pick some drop-down menu or something. But generally, a lot of times they're multiple choice. Now, when you're doing the homework, you should be drawing the pictures, because on a test and a quiz, I'm going to want you to draw pictures like we'll do today. And so I think the reason people often end up not doing well in this material is because you don't practice it the way I'm telling you to do it right now. When you see a problem in the homework, you should draw a picture and then match your picture up to the picture on the page. If you're just looking at the picture and then you're like matching multiple choice style and, just so you can get the right answer, that's not helping you. It helps you get like 0.00% of a grade point on your final average, but it's digging yourself into a hole on a test. So I can't stress that enough. Please draw some pictures in your notes when you're doing this stuff. Lots and lots of pictures. Questions before we look at how we do some of this? Thoughts about any of these pictures or anything? Okay. So let's look at the first page. The first page of this transformations section is all about shifting vertically and horizontally. And what I'm going to do as we go through this is I'm going to explain the concept, but I'd like to sort of also try to explain the intuition behind the concept, so you don't have to memorize things, right? Remember we talked about that. If you just kind of understand why things are true, then you don't have to memorize them. They just make sense, right? So the first thing is vertical shift. This is the one that's usually the easiest to learn, so that's why it's first. And so what we have here in our pictures and what this box is showing us is that if we have c, which is some positive number, if we add c on the outside of a function, so we take a function and we add c to it, it moves that function up by c. And if we subtract c from the function, it moves the function down c. So, and that's what's being shown in this picture. If this is our original function, the bottom one, the blue one, then adding c on the outside shifts that thing up by c. And if we take our function, which is blue, and we shift it down, and we subtract c, it shifts it down that many. So for example, let me do a quick, and in these following examples, I am going to draw two pictures. I'm going to draw the original in dotted red, and I'm going to draw the transformation in solid blue. I guess it's the opposite of what these are. Maybe I should have switched that. Too late now. Okay. So let's do x squared. So x squared we know looks like this, and I know that because I've memorized that front page. All right. If you don't believe me, x squared looks like a u, right? Looks like a u. If we add a number on the outside of it, like x squared plus 5, it just takes this graph and it moves it up, however many units we add to it. So x squared plus 5 might look like this. The exact same graph, or at least I tried to draw the same graph, but it moved up 5, and so the new intercept is up here at 5. Right? It used to be down here at 0, and now it's up here at 5 because we added 5 to it. And think about why that's true. X squared are the y values. When we plug an x into x squared, a y value comes out, right? And so if we add 5 to x squared, it's like we're adding 5 to every single y value. And so if you add 5 to every y value, it just shifts the entire thing up 5, right? And similarly, if we subtracted 5, it would do the opposite. So let me draw x squared minus, use a different number. Let me do x squared minus 6 or something. Right, this is what x squared minus 6 might look like, where the new intercept is down at negative 6. Again, we just took every y value and we took 6 away from it, which is just going to move the whole thing down 6. And so going back to the things I'm looking for, right, we've got the correct shape, we've got the shift up or down, and I wrote the new intercept. And so I've got those three things that I'm looking for. Questions about this idea? Right, so this one's, like I said, this one's the most straightforward one. If you just add a number outside of it, it moves it up or down, depending on whether it's positive or negative. Okay, let's look at the next one. Is everyone set with this one? So that's a vertical shift, right? This is a vertical shift. The next one is talking about horizontal shifts. So a horizontal shift is left and right, obviously, right? And so again, let's pretend c is a positive number. If we plug x minus c into a function, that will move the graph to the right c. And if we plug in x plus c into a function, that moves that function to the left. So there's two things I want to point out about this. First of all, this is like a composite thing, right? This is from test 1. This is a composite function where you're plugging one function into another. This is just like that x plus h problem from the test that I just handed back. That's one thing I want to point out. The other thing I want to point out is it's kind of counterintuitive, this one. You know, usually when we associate negative with moving to the left, I would think. That's how I associate it. But when you plug in a negative x or a negative c, it moves it to the right, actually. And a plus moves it to the left. And so it's kind of counterintuitive the way those things work. So keep that in mind. But, well, yeah. And so this is what it looks like pictorially. If this is our function, f of x, then if we plug in a negative c, it just moved that thing to the right c. And if we have f of x as the blue, and we plug in an x plus c, it moved it to the left. So let's look at one, let's look at an example. Question? Yeah?
C is just a variable to represent a number that is plugged in.
It's some number, yeah. So we'll see, so for example, let me show you one and then you can let me know if it makes sense. So c is just a number, so let's pretend we had x cubed. So this is what normal x cubed looks like. And so if I plug in an x plus or minus some other number, it's going to shift that left or right. And so for example, this graph has been shifted to the right, and this might be x minus 3 cubed. See how that's in the x minus 3 is inside of the x cubed, which is what makes it a shift to a horizontal shift rather than a vertical. Right? On the previous one, the plus 5 was added outside of the x squared. Right? The plus 5 is not being squared in the first one. But in the second one, the x minus 3 is entirely inside of the x cubed, which is what shifts it to the right. Yes?
I was just going to say, so in the situation where you got rid of the parentheses, it would look like that, but it would be shifting up.
If the minus 3 was not inside there?
So if it wasn't in parentheses, it was just x minus 3 cubed, then in that case it would look like that, but it would be shifting down.
If it was x cubed minus 3. If it was x cubed minus 3, it would be shifting it down. But if it's x minus 3, parentheses, cubed, it's moving it to the right. And to give you some intuition about why that works and why it's kind of counterintuitive, when we plug a number in for x, like we plug in 0, for example, it actually plots the value at negative 3 instead of at 0. And so when we plug in 0 into this function, it actually reaches over and it grabs the value at negative 3 and plots that instead. And so that's why it plots this one at 0 instead of this one. And so this one gets plotted, which it moved over. See that? When you plug in a value, it actually plugs in 3 less than that value, which is 3 to the left, and so it pulls it over to the right. Let's write down the intercepts. So I'm going to start with the y-intercept. Does anyone remember how we do intercepts? We learned this in the line section. Remember, Tom?
Plug in 0 for x and whatever you get as your y-intercept.
Yeah, good. So for the y-intercept, you plug in x equals 0 and see what happens. So you have y equals 0 minus 3 cubed, which is minus 27. And so this new intercept down here is going to be at minus 27. So we have that new intercept. And so then the opposite, we do the opposite for the x-intercept, right? If we want to know the x-intercept, you plug in y equals 0. And so if we plug in y equals 0, we get 0 equals x minus 3 cubed. And so that means x minus 3 has to be 0. And so that means x is 3. And so this new x-intercept is 3. So I've got my shape correctly, I have shifted it correctly, and I have my intercepts. So those 3 things. Questions?
Would you be able to, like, just get rid of the cube
I'm sorry?
on the very end?
Oh, on this one?
Yes.
I took a cube root. I did like a cube root right there. Yeah, so to solve that equation, we take a cube root to get rid of the cube, and we get what's inside there. The other way to think about that is, if we want to cube something and it end up being 0, then whatever we're cubing needs to be 0. You can't cube a not zero number and get 0, and so that means x minus 3 has to be 0. That's the other way to kind of think about that. And the other thing I want to point out is, do we really need to do that at all? Why not, Nick? I know you know it, so just be a little more explanatory.
I'm actually not sure why.
Oh, I think you know.
Oh, no, I forget.
Yeah, I know you knew it. It was right there. You were like real positive about it. Rachel?
Because it's the C value.
Yeah.
And whether it's negative or positive determines how far it shifts or which way and how far.
Exactly. Right. So the intercept used to be at 0, 0, and we shifted the graph to the right 3, and so it moved over to 3. Right. So this x minus 3 is, since it's a horizontal shift, it just shifted the x-intercept horizontally. Right. For the same reason that we didn't need to do these up here. We could have solved for those intercepts, but I just knew that it moved from 0 and it moved down 6, and so we didn't really need to do the algebra there. I just wanted to show you this one just to be clear about how we need to do that in problems where it's not as straightforward. Like on the next one, for example, we won't be able to just do that one. So let's look at the next one. So I want to do an example that uses both of these things. So let's graph the following. F of x equals absolute value of x plus 5 minus 2. So this first page, this reference page of all these graphs is important, right? Because we need to know the shape that we're moving around. We start with one of these shapes, and then we shift it around up and down, left and right. We'll flip it, we'll stretch it, etc. So what graph or what base function are we using? What are we going to shift around? Yeah, absolute value, right? We've got the absolute value in this problem, and so this is a transformation of this graph. It's an absolute value graph. And so that's the first thing I want to write down, is that we are going to transform absolute value. And so that's important too, because then we need to compare this function to the absolute value. What's the difference between what's written down here and the absolute value of x? For one thing, there's a 2 subtracted from it, but what else? Andrew?
There's the plus 5.
And there's a plus 5 inside of it. And so maybe Andrew can tell me, what's that plus 5 doing?
It's moving it to the
Yes, this is shifting absolute value to the left 5. Because we have an x plus 5, and it's inside the absolute value. This is like if f of x was absolute value of x, f of x plus 5 would be absolute value of x plus 5. So this is a left shift, again, because it's inside the absolute value. Because the minus 2 is outside of it, that's what's moving it down. And so this is going to shift absolute value down 2. And so I know absolute value looks like a V. So I'm going to write that down first. It's got that corner. That's what absolute value of x looks like. And so we're going to move this thing to the left 5 and down 2. And so I already know like where this vertex is, right? You call the corner there, that corner spot is called the vertex. And so instead of being at 0, 0, where is it going to be? It's going to be at -5, -2, right? Because we move left 5 and down 2. And so it's going to be over here at -5, -2. Oops, let me use a different color. Sorry about that. And I know it's going to be a V. It's going to be the same shape. So it's going to look like that and like that. All right, so this is the point -5, -2. Questions about that part so far? So let me just mention why I care about this. This might seem like not, why do we care? We have graphing calculators and stuff. Because when you use a graphing calculator, you want to be able to catch your errors, right? Especially if it's a more complicated function. And so knowing the shape of what it looks like and kind of having an idea what it looks like is actually really important to catching simple mistakes. And you also kind of want to know what a function looks like before you do anything with it. It helps to know that this starts at -5, -2, and everything is above that point. Like that might have some meaning for your function. And so having an intuition about what the function looks like can be really, really helpful and important sometimes. And so in other words, we don't use this method to draw really nice pictures. We use this method to kind of have an idea of what the function looks like before we do anything with it. That's the important part of this. And so I'm not looking for nice drawings, right? I won't draw a single nice drawing. I don't know how. And I'm not expecting you to. I just want to see those three things: the right shape, shifts, intercepts. Okay, so let's do the intercepts. And this isn't an obvious one. I don't know what those intercepts are because it's kind of confusing, right? So let's solve for them. So the x-intercept, you let y equal 0 and solve for x. And on the x-intercept, you let, for the y-intercept, you let y equal 0 and solve for y. Oops, I forgot to write y-intercept. And so when I let y equal 0, I'll do that one first. You have x plus 5, absolute value, minus 2 equals 0. This is a question from the first test. Right, this is how do we solve an absolute value equation. This is why we talk about doing that. You add the 2 to the other side. And now we have this form. A lot of people struggled on this question, so this is maybe a good review. Now we write down x plus 5 equals the positive 2, or x plus 5 equals negative 2. And we solve both of those. And so we're going to get 2 answers. And that makes sense because if we look at our graph, it looks like we should get 2 answers. There's 2 x-intercepts. And so I usually like to draw the picture before I draw the intercepts because it helps guide me solving the intercepts. Like I already know that I'm looking for 2 negative intercepts. That's x-intercepts. And so hopefully I get 2 negative things out of this, right? And it looks like I will. So I get x equals negative 3 or x equals negative 7. And so that's good because it looks like I should get 2 negative intercepts, and I did. Right? So that's helpful. Helpful to draw it first, I think. And then on the y-intercept, if we let x equals 0, we just get y equals 0 plus 5 minus 2. And so that's going to be positive 3. And so this is a positive 3 right there. And again, that's good because it looks like it should be positive, not too far off the x-axis, so 3 sounds about right. All right, so in other words, matching your sort of visual interpretation of what the shifts are with your algebra is a good final check to make sure you did things right. In other words, if I got some positive number for an x-intercept and I looked at my graph, I should know that something's not right. Either my graph isn't right or my intercept wasn't right, one or the other. But it matches up, so it's good. Questions about this idea? This page at all? Yeah.
So, by the time you are draw the graph here, which one do you advise us to do? Do you want us to kind of intercept first,
I think it makes sense to draw the shift first because you're going to know what the shifts are, like left, right, up, down, flip, whatever it happens to be. So I would recommend sketching the graph and then thinking about what the intercepts are secondary. That's in my opinion the best way to do it. But you can play around with them and try it yourself and see you may like it differently. I don't know. Other questions? All right, let's look at reflecting. So when we reflect graphs, we're talking about flipping them over, and either flipping them upside down or flipping them side to side. And I had a really great question in my morning class today, which was, if there's more than one thing to do, like on that last question, there was more than one shift, we shifted left and then down. Does it matter whether you shift down and then left or left and then down? Not in shifts, but in reflections it does matter. And so I just want to make a quick note here. This is the only time it matters with this stuff. You usually want to reflect before doing other transformations. Just keep that in mind. Whoops, transformations, if I can spell it quick. I swear, whenever I'm starting to do a video, I can't write or spell. So just keep that in mind, and you can think about that. If you flip something upside down and then shift it left, it's different than shifting it left and then flipping it upside down. And so we want to reflect before we do those things. Keep that in mind. There's only a couple times that'll be an issue, but keep that in mind. Okay, so here's how these two things work. So we've got our function f of x. If we multiply the function by -1, it reflects that function about the x-axis. And so that's what's being shown in the left graph here. If we have f of x and multiply it by -1, it takes this function and it flips it upside down like this. So this like this, right, over the x-axis. And you can see that's what's happening between those two graphs. And notice that the negative sign's outside the function. If we multiply the x inside the function by -1, that reflects the graph around the y-axis. And so that's like starting with this one and flipping it over to this one, around the y, like this, right? And let's think about why that is. Again, f of x kind of represents y values, right? It's all the y values. And so if we multiply all the y values by -1, it takes the positive ones and makes them negative, and it makes the negative ones and makes them positive. And so that's what gives you this kind of flipping action, because it just literally flips, makes them opposite, right? And so I'm going to write that down. I really think it's super helpful to just understand that rather than memorizing it. And so minus f of x, it takes all the y values and multiplies them by -1. And in doing so, that flips the graph upside down. So I refer to that as upside down, like over the x-axis, upside down. Similarly, if we multiply all the x values by -1, that's what's going on with this f of minus x. It makes all the negative x values positive and the positive x values negative. And so it does the opposite, where we're doing this kind of flipping instead, because we're flipping over with the x values, right? So let me write that down. So 2. F of minus x, when there's a minus x inside the function, that takes each potential x value and instead uses the minus x value. Right? So if you plug in a 2, it's actually going to plug in a -2. And if you plug in a positive 10, it actually plugs in a -10. So it does the opposite sort of flipping, where it flips it from side to side. And so thus, it flips the graph horizontally. And then I'll just try to use the more precise term. Upside down is really vertically. Try to be more precise about that. Questions about that concept? Before we look at a couple of them. So what about this one? Let's look at square root. So I'm going to draw the square root of x. I know square root looks like this. If it's an even function, right, it kind of like slowly increases and then it starts to flatten out. And so that looks like this. That's what square root looks like, square root of x. And so minus square root of x would do that same thing, but we'd flip it upside down. Oh gosh, I just did it again. Vertically. Because we flipped it over the y-axis, or the x-axis, excuse me. All right, we just took every y value and we made all the positive ones negative. And so it flips over like that.
Is this different than graphing quadratics or polynomials?
This is different than graphing polynomials, yes.
How's-
We're going to
I
do
know
that
that's
too.
Different, but like how's that?
Because polynomials, so this is different than graphing polynomials because every polynomial, when you have a different degree, doesn't fit any of these forms. Like, it's not like we're just adding a number on the outside. We're like adding an x squared or something like that. And so that's a completely different kind of thing. And to do that, what we do is we find zeros and we test points in between the zeros. We're going to do that literally in the next section, I think. So we'll see that. Yeah, go ahead though. You have a follow-up?
Yes, that when like we find the vertex and everything.
I'm not sure what you're referring to. That might be that might be this. Anyway, we'll see that though. Let me just draw one more. We've got 1 minute left. I want to draw one more picture to drive this home. So let's do absolute value, or square root one more time. And I'm going to do both of them. So let's do square root of minus x. So that's going to be this. See how the minus sign is inside the square root compared to outside? Why is it, that looks weird though, doesn't it? It almost looks like we're plugging in a negative number into square root. Why is that okay? Yeah, because we're plugging in negative numbers. So when we plug negative numbers into x, they become positive by that negative sign. So that's why it's over this way. But anyway, intuitively from this, we flipped it like that because we plugged a negative x inside. Let me do both real quick. How about this one? What equation would this one be? So I just took that last one and I flipped it vertically.
Negative square root of negative x.
Yeah, it's both of them. Right, we flipped it both ways. And so you could think of flipping it sideways and then vertically, or you could flip it vertically and then sideways, and you would get to that graph both ways. So let's look at another one with, we'll combine another one with a couple. And let's stick with absolute, or a square root on this one again. So let's start again with square root of x. And let's think about let's do something from the last page and this page. So what is the minus square root of x plus 4? Obviously we're in a square root situation, right? We're starting with the square root, but we have a negative 1 on the outside of the square root and a plus 4 on the inside of the square root. And so just looking at this page, right, this negative 1 on the outside flips it vertically. So that's going to flip square root of x vertically around the x-axis. And so that's something on this page. So we know that whatever this looks like, it's going to be an upside down version of what I drew here. What's the plus 4 do? That's something from the last page. So that's a plus 4, an x plus 4 inside of the square root, right? So I don't have an idea what that does. It's a shift. It's some sort of shift, you know? So if the plus 4 was outside the square root, it would move it up. And so instead of up, what's the other one? Yeah, to the left. Because it's inside the square root. That's an important distinction. If that plus 4 was outside of the square root, it would move it up. But because it's inside, it's going to shift square root to the left 4. And remember, this is that one that's a little counterintuitive. Usually, I don't know, when I usually see something that says plus 4, to me, I want to move it to the right, because plus means to the right. But so just remember that it's the opposite in some sense of what you might think. And so what we're doing is we're taking the square root and we're going to flip it upside down because of the negative, and then we move it to the left because of the shift. Is that okay? And so it's going to be an upside down version of that. So just, think with me what it's going to look like. You flip it upside down, and so it's now it's down here, but then we're going to move it to the left as well, and so it's going to be over here going down like that. So that's what minus square root of x plus 4 might look like. Questions? And so I wrote this down on the first page last time, but I'll just remind you, the three things I'm looking for are the correct shape, right? Any shifts that take place, and then any intercepts that exist. And so we've got two of those, right? We've got the shape, it looks like a square root shape. We did the shift, we flipped it and we shifted it, so that's good. And now we just need to figure out what the intercepts are. And so I'll remind you, when we figure out what the x-intercept is, you set y equal to 0, right? And so we do minus square root of x plus 4 equals 0. That's how we figure out what the x-intercept is. And we can solve that for x. And so we can square both sides, and we'll get x plus 4 has to be 0. And so that means x equals minus 4. So that point right there is at minus 4, 0. And note that we didn't really need to do the algebra to get that. I want to always just remind you that's how we can get an intercept without thinking about it, or without conceptually thinking about it. But we could have gotten that without doing any of this algebra, right? Because we flipped this. It used to be at 0, 0. The x-intercept used to be at 0. But when we flipped it upside down, right, when we did the flip, it's still at 0. It would have been right here going down. And then we moved it to the left 4. And so this minus 4 is because we moved it to the left 4. Right, so we really didn't need to do this one so much. But for the y-intercept, I don't know how to think about that one. We can't really get an easy way to think about where that is. And so we really do need to do some algebra for that. So for the y-intercept, you set x equal to 0. And so you get y equals minus square root of 0 plus 4. And so that's going to give us minus 2. Whoops, sorry about that. Off the page there. And so it's a negative number. And so I usually like to draw the picture first because it makes me feel good that that's a negative number, right? Because it looks like it should be a negative number. It should be negative 2. That looks like it's good. So that's a negative 2 right there. All right, and those are the three ingredients that we're looking for. Questions at all? So just kind of as a reminder, and if you page through the next couple pages, you'll see this, but you know, we're going to add a little more complexity every time, right? We started with shifting left and right, up and down. We're now flipping things, and then on the next 2 pages, we're going to be stretching and shrinking. And so I'm just saying that because if anything's a little unclear, we're just going to add kind of more complexity every page. And so this is really a great time to ask questions, even though it's 8 o'clock in the morning and you might be a little bit tired. If you're a little confused about anything, by all means, shout it out there. That'll help you wake up, too. Thoughts? Yeah.
So when would the graph be shifting like up and down? Would that be different?
Yeah, so I know you weren't here last class, but if you turn to the previous page, adding and subtracting numbers inside and outside is what moves it up and down. And so inside is what moved it left and right, because the plus 4 is on the inside of the function. If it's on the outside, we move it up and down. And so let's look at one like that right now, too. And if you haven't downloaded those notes from last class, you should take a look at those. Let's look at a cube root function. So let's start with the cube root. I'm looking at this page. I want to do a cube root thing. And so cube root, remember, looks like this. So it looks like the square root, right? Like if we covered up the bottom half, it looks just like the square root, except we also have this bottom half, because you can plug negative numbers into cube roots. So let's start with the cube root, and let's shift that one. So it starts like this, does this kind of thing. That's what the cube root looks like. And so let's draw a transformation of that, and let's do the cube root of minus x minus 1. And so just looking back on the last problem and that last question that you just asked, notice the difference between this one, how the plus 4 is inside of the root, but on this one, the minus 1 is outside of the root. And so that's the difference between moving up and down and left and right. So in the last one, because the plus 4 was inside, we shifted to the left. But now because the plus 1 is outside of the root, that shifts it up or down. And because it's a minus, it moves it down, right? So this minus 1 is now going to shift the cube root down 1. And so we're going to start by thinking about shifting it maybe down, right? I forget what I was going to add to that. Does everyone see the difference between those two things? That's the one that usually ends up confusing people. Oh, I remember what I was going to say. Remember, because if we just subtract 1 from a function, it's like we take every y value and we subtract 1 from it. So that's what's taking it down. But when it's inside the radical, we're taking or adding or subtracting values from the x's, and so that's what shifts it left to right. It's the difference between adding or subtracting to the x's or adding subtracting to the y's. Okay, so the minus 1 shifts it down. That's from the last page, right? From the previous page, from last time. What's the minus 1 do? That's inside the cube root. That's from this page, right? So what do you do if there's a minus 1 that's multiplying the x inside of the function? Okay? Yeah, that's what this property is right here, right? See how the x is being negated inside of the function? So that's this situation where the x is inside there. And so this is going to flip the cube root horizontally instead of vertically. Again, just compare it to the last one, right? This negative sign on the previous one was outside the root. That's what flipped it vertically. This one is inside the root, which is what flips it horizontally. Right? Notice the difference there. And so we're thinking about taking this original and we're going to flip it horizontally, right, and shift it down 1. And so I will do my best impression of that, making it a little bit lower. You can already kind of imagine what it would look like, but it's going to look something like this. Right, you can see I tried to make it a little bit lower than this one because it moved down 1. It also shifted, it flipped horizontally, and so it's going the other way. And because it shifted down 1, we ended up getting a couple more intercepts too. Questions about the picture first? Because the picture is usually an important first step. And then you think about the intercepts, because now when I have a nice picture, I'm looking at this and I think, okay, I need some negative x-intercept and some negative y-intercept. And that's very helpful to kind of just know that. But you kind of need to be able to draw the picture before you get that information. So are there questions about that? All right, so let's do the x-intercept. So the x-intercept, you plug in y equals 0. So you do 0 equals cube root of minus x minus 1. If we're going to solve that equation for x, we want to isolate x, right? So we're going to add the 1 to the other side and get that. We want to get, sorry, that's a minus x in there. We want to get rid of the cube root, and so we cube everything, right? We cube everything on both sides, and then we get 1 equals minus x. And so that means that x equals minus 1. So that's good because it's a negative number and it looked like it should be negative. And so it fits our picture very well. And so that's an easy way to get the x-intercept. And then the y-intercept, it's usually a little bit easier because you just plug in x equals 0, right? So cube root of minus 0 minus 1. And so you just get y equals minus 1 as well. And so the two intercepts are at minus 1s, which is just a coincidence, right? They usually won't be the same. It just kind of worked out that way. Questions at all? So just to summarize here, what we've done so far in those first 2 pages is we've shifted things up and down, left and right. That was page 1. We've flipped things horizontally and vertically. That was this page. And now we're going to stretch things and shrink things vertically and horizontally. That's what's on the next 2 pages. And quite frankly, those are the more complicated ones. Those are the in my opinion, the harder ones to sort of visualize, and they can be a little tricky to draw sometimes. But anyway, we'll move on. Are there questions about this page? Is everyone all set with this page?